Hello, my name is Nandor Licker. I'm a PhD student at the University of Cambridge, and last summer I was an intern working on building an interpreter to evaluate constants in Clang. When I started on the project, I assumed I'd be writing a Constexpr interpreter, but very soon I found out that Clang not only evaluates Constexpr, but it tries to evaluate every single constant it finds in the source code. And this is quite useful, because if we have some constant that we generate using regular operators that might result in unified behavior, it's a good idea to emit a warning out of it. And this happens sort of on a best effort basis and leads to some interesting semantics because the functionality has to be shared with context evaluation. So constant expressions actually appear in some contexts, such as templates. And in this case, the compiler cannot compute constants on the best effort basis anymore. It must evaluate every single constant that appears in the program. What makes this project interesting is all the uncertainty behind evaluating constants, because the definition of what is a constant used to be a bit funky in the past. So, for example, if we try to run this with the C++ 2003 standard compatibility mode, then we get a warning from the integer overflow. However, this was fixed in C++ 11, and if you're running in that mode, then we need to emit an error because the multiplication results in undefined behavior, and that's not allowed in Constexpr. So besides specifying quite accurately what it means for an expression to be constant in C++ 11, the standard also allowed a lot of stuff to be Constexpr. So we can write code like this, which might be useful for some people, but from a perspective of a compiler, it's not easy to deal with these kinds of statements. And then things became more interesting with every revision of the standard. So in C++ 14, we can define the hash function like this with a beautiful loop that mutates a local variable and then returns its value and reads from memory and does a lot of interesting things. C++ 17, I like this particular version of the standard because it didn't do much to Constexpr. But then C++ 20 came along, and even though unions were allowed in C++ 11, the active field couldn't be changed. And that could have simplified implementation. But in C++ 20, of course, we can change the active field. And that leaves the objects in a very interesting state. So in this particular case, we need to say that we are reading an uninitialized object. And basically, Constexpr seems to be, it's a moving target. More and more of the language is allowed in a Constexpr context. And presently, evaluation is done using a tree evaluator that walks the AST. And while this evaluator is flexible, it is painfully slow. For example, you can consider this a fairly simple for loop. And we can look at the statement that's repeated most often in it, which simply tries to read an accumulator. It simply tries to add the value from the vector to an accumulator. And in the AST, which the evaluator needs to walk node by node, we have a node referencing a local variable, but this node cannot read its value. It must produce an L value reference to the value, basically a pointer. And only then is the evaluator allowed. Only in the L value to R value in the cast is the evaluator allowed to actually read the value of the location. And same happens with the pointer. We need to create an L value, read it, with the index L value, read it, finally apply the subscript operator, which generates a pointer again that needs to be dereferenced. When we have two R values, we can finally add them. And after producing an L value for the left-hand side, the assignment can be evaluated as well. And we can see that this is not particularly efficient because there are a bunch of nodes in the ST, And we need to produce quite a few temporaries that are not compact and require a fair bit of work to set up and tear down. And this is a place where an interpreter can do trivially better. So I chose to build a simple stack-based interpreter with well-typed opcodes. For the same example, the interpreter would traverse the AST, but when it sees that there is an L value to R value cast operating on a local variable, instead of creating a pointer and temporary, the interpreter can emit an instruction that fetches a 32-bit integer and pushes it on the stack directly. Same goes for the pointer. We can load it. We can load the parameter from some storage and push it directly on the stack. The loop index, yet again, we can emit a single instruction for it. Presently, the subscript architecture is implemented using two bytecode instructions. Addition is yet again quite simple. And when we assign to a local variable, we don't need to generate an L value. We can simply set the local once we computed its value. So instead of having to traverse more than 10 nodes in the AST, in the performance-sensitive loop, the interpreter can repeat 7 instructions. And most importantly, bytecode is optimizable. A tree evaluator could be optimized as well by better matching on the AST, but simply expressing that using the Clang AST is a bit of a pain. However, in the bytecode interpreter in the future, a bunch of people optimizations are possible. So for example, the array index operator could be lowered in the future to a single expression. Now, there are a few aspects which make the Constexpr interpreter a bit unusual. And the first problem is the fact that in the interpreter we need to lower C++ to something. And Clang already lowers C++ to something in quite a few places in the compiler. So obviously we need to generate LLVM IR from C++, and that lowering is quite big. Next, I understand that the Clang static analyzer has a lowering from the AST to some intermediate representation. And finally, we have the tree evaluator, which generates constants from the AST. Now, if we add the bytecode interpreter, then we need to add another lowering from the C++ AST to bytecode, and then we need to go from bytecode to constants. And this is a bunch more code in the compiler. And ideally, we wouldn't want to bloat it too badly. The problem is that we can't simply replace the whole evaluator with the bytecode compiler, because there are places where the bytecode interpreter does quite well. For example, if you have a top-level constant that's computed as 1 left shift 20, then if you were to compile it to bytecode, save the bytecode to memory, and interpret the bytecode, we'd be doing a lot worse than the interpreter which walks 3 nodes and performs the addition. So to kind of have the best of both worlds, the Constexpr interpreter has a C++ to something lowering that's parameterizable. It's a class called bytecode gen and bytecode statement gen that's parameterized by an emitter. And currently there are 2 emitters. There's an evaluating emitter whereby which evaluates instructions as they are emitted from the AST walker, computing values directly. It doesn't have to store the bytecode into memory. It doesn't have to invoke the interpreter to evaluate the bytecodes. It just runs them as the tree evaluator would. And the performance of this is roughly similar to the performance of the existing tree evaluator. But for functions and for bits of code that we expect to run many times over in a Constexpr context, there is a bytecode emitter which does the expected thing. It emits bytecodes to memory, and then it invokes and then when a function call is encountered in a top-level context, it starts interpreting the function's bytecode. And this allows us to in the future, my hope is that the bytecode generator with the evaluating emitter completely replaces the existing evaluator in Clang. But now what makes this project really exciting is this bit of the C++ standard, which says that an expression is Constexpr or a constant unless its evaluation results in undefined behavior. So basically, the compiler's Constexpr evaluator needs to be the ultimate sanitizer. It needs to do what asan does, msan does, and a bunch more. Yeah, this is like the much more corner cases. And in some cases, this is easy. Integer overflow, doable, null pointer dereferences, simple if statement. All nice. But we can write stuff like this. C++ allows us to generate a pointer one past the end of an array, which is a bit tricky because that address might not really point to actual allocated memory. Also, we can have externs, which we really know nothing about. We cannot read them from a Constexpr context, but we can generate all sorts of pointers to them. And these problems sort of shape the memory layout that the interpreter needs to represent all the allocations that can happen in Constexpr. Besides stuff that's illegal, there are things that happen to be legal. And sometimes it's easier to ban some operation than to allow some other operation to take place. So for example, I hope nobody writes C++ like this. I hope nobody writes C++ like this in Constexpr, but the evaluator and the interpreter need to run this bit of code. If you haven't noticed, the bit that makes it funny is that in the constructor we dereference we look at the previous element with the this pointer. And because we have an array and we make sure that the first element's initializer doesn't look at the -1 index, this code must run fine. Yeah. So to illustrate the problem a bit better, we can look at the memory layout of a structure where we have an array of integers, an array of structures, and a float. And ideally, on a target, we'd like the items to be laid out sequentially in memory, maybe with some padding in between. And starting from the identifier of the structure, we can derive legally a large number of pointers that are all illustrated. And many pointers, as you can see, the addresses of most of these pointers are equal. However, what these pointers can access is different. So 2 pointers might have the same address, but when they're incremented, they behave differently, and when they're dereferenced, they behave differently. So we can write a function that sums up elements given a pointer to integer, and a number. And we can ask it to sum up 4 elements starting from the array of 3 elements that was inside the structure. We can derive a pointer to s.a legally, and we can read from it. S.a plus 1, it's legal, readable, a plus 2. We can derive it, read from it, no problems. S plus 3, this is 1 past the end, so we are allowed to derive it, but we're not allowed to read from it. And the problem is that the same memory location can be legally referenced through a different pointer, but not with this one. So yeah, pointers which are the same or not really the same. The address is not enough to differentiate 2 pointers. And the way the interpreter deals with this case is by making sure that pointers which are different are actually different in their representation. So first of all, in orange and in green, we have metadata. Qualifiers such as const, volatile, and mutable are per storage location. And this inline metadata is used to store those qualifiers. Whenever we dereference a pointer, those bits need to be checked to make sure that the access can happen. Because, for example, Constexpr allows constant cast. So we can allocate a constant array of integers, we can cast it to an array of integers, and then when we try to write to it, we need to emit a warning saying that we're trying to write to read-only storage. And these bits are located in the inline metadata. Unfortunately, because the inline metadata is there, by default, all the addresses are disambiguated. And this helps ensure that all pointers are unique. Now, this layout is a bit more compact than the existing layout of the evaluator, which I believe uses hash maps or something similar to represent fields of structures, whereas we lay them out segmentally in memory. Granted, there is some padding in between the elements, but at least they are consecutive. They're not located at random locations. And most importantly, primitive arrays are handled much more efficiently, because as you can see, the array of 3 elements, the elements are laid out one after another in memory. And I expect this to help performance a lot. Now, when something goes wrong, useful diagnostics should be emitted. And this requires a lot more metadata. So while the inline metadata is generated for each allocation, a lot more, a whole graph of descriptors is generated at compile time to describe each structure, each field, and to allow the compiler to identify where memory comes from when an invalid access is executed. So even though this is more compact than the existing implementation in Clang, the language doesn't allow a great implementation. There is a need for a bunch of metadata. What makes things even worse is the fact that pointers can reference objects which are out of scope. So for example, we can have a createZombies function that allocates local on its stack, and then references to that local are returned. And the implementation of this has a bit of an overhead because pointers in interpreter are basically fat pointers. Each allocation site, pointers are part of an intrusive list, allowing each allocation site to track the pointers which point to it. So when the object goes out of scope, we can invalidate all pointers to make sure that when they try to dereference the block, which might have been freed, fail. Now there's a problem in the interpreter. Stack frames are destroyed when a function returns, which means that the block which stored the value 0 is going to be deallocated after return. To make sure, also pointers require, in the current implementation, pointers need to point to actual memory. Pointers have a field called the offset, and the offset needs to point past the inline metadata. And if the allocation goes away, then those pointers will point to freed memory. So when a function tries to return and some of its locals still have pointers on it, the data is copied into global memory and the pointers are adjusted to point to it. If pointers are, then the original allocation site from the frame is destroyed. And if pointers go out of scope, then they're simply removed from the list of references. If somebody tries to read from the block now, then that's going to result in an error in the interpreter. If all pointers go away, then that block can finally be deallocated. Basically, this works quite well if nobody returns a reference to local. If a reference to local is returned but not used, there is some overhead. But in general, the encouragement is for people to write correct code. Well, not correct code. It's not to do silly things. The goal is to make reasonable stuff fast. Silly things are going to incur a massive performance penalty. And for reference, this is how pointers look like. They're 24, 32, 48 bytes in size. Yeah, they're quite big. Most notably, they are not the size of uint pointer t, which raises lots of problems with GCC, which allows, in a constant context, casts from pointers to integers and then back to pointers. So the interpreter is very much a work in progress. I have committed an initial patch that showcases the two emitters and plugs the interpreter into Clang, gated with a feature flag. Have another patch coming up that implements roughly 70% of C++11, most of the looping constructs from C++14, and some vtable mechanisms from C++20. However, the to-do list is still quite long. Out of the 15,000 tests in Clang, 450 are still failing, thanks to GCC, Objective-C, and all sorts of extensions. And I'll need to do a lot more work on implementing built-ins, and once I'm done with that, I need to implement more built-ins, and once I'm done with those built-ins, there are going to be even more built-ins to implement. Compile writers seem to very like built-ins, but yeah. When you start from scratch, it's not particularly pleasant to implement them all, especially when there are some built-ins along the lines of built-in string length, built-in memcopy that are allowed in a Constexpr context. And I expect people to use them at some point, so they need a fast path. So for example, if string length works on is invoked on an array of characters, we want it to be as fast as the actual string length. If it's invoked on a structure, then I'm actually not sure what should happen, but if that's allowed, it won't run fast in any way. It's going to be a fallback to slow path. And yeah, I am not a big fan of GCC. I can't help but mention a construct called built-in constant p that does, I still don't know what it does, but it allows pointers to be cast to integers and back to pointers. Yeah, it's fun. And finally, so this benchmark is this is the ideal case. If we have a loop with a bunch of integer operations, then we can do 10 times better than the interpreter. I report more performance numbers as soon as I can get more of C++ to run. The idea is that I'm working towards feature completeness, and then performance will be brought up to the level of the existing evaluator. So memory-wise, I hope to lower the memory footprint of constant evaluation because the memory representation in the interpreter is much more compact than the AP value representation present in Clang. And this is mostly achieved by allocating objects segmentally in memory. So for example, an array of 10, okay, an array of a few elements is going to actually be an array of a few elements. Finally, I would like to thank the people I worked with. Also, thanks to people who commented on my patch and helped me fix issues on PowerPC, Visual Studio, GCC, and ARM platforms. Because when you commit 3,000 lines of code to Clang, you're bound to break a lot of stuff. And questions?
If anyone has any questions, if they could come up to the mic.
So the classic demo / benchmark that I've seen David Vanderveer do on this is he takes those loops at the end that you had and changes the integer into a thing with an implicit cast operator to an integer and shows how the compile time goes way, way up. Do you have that same problem, or do you have any idea of what the cost difference is between those two?
Well, an implicit cast in the interpreter would be an instruction that runs the C++ implicit cast underneath. So
you're still going to pay for it. There's no actual optimization or anything of it away, but it's less, or like how much less, how much more?
So first of all, integers are actually integers. In the evaluator, they are represented using AP value. They allocate a lot. So in the interpreter, what would happen is that like if we have a cast from a 32-bit number to a 64-bit one, then we pop 8 bytes to the stack. The stack is 8 byte aligned. And then we push 8 bytes that represent the 64-bit number, and that's it. I would expect that to be faster than the evaluator.
Hi, I had a question about the padding that you introduce to make sure that like a pointer to a struct is not the same as a pointer to one of its members.
Yep.
Is there anything to prevent, like say, if the program has knowledge of this scheme, that it could basically do pointer arithmetic to access one of the members from the pointer to the struct? Do you do anything to prevent that, or is that just kind of best effort?
I hope not. That would be a bug. So basically, the inline metadata allows the pointer to identify exactly by how much it can be incremented.
Right.
So if you try to do so if you have a pointer to an object and we try to do +1, that's fine, but +2 would be wrong, because the inline metadata says that the pointer to the object is a pointer to an array of a single element.
Yeah, that makes sense. Do you allow any kind of round tripping from pointer to integer type? Do anything like that?
So I have a plan to implement that. Basically, while compiling, the compiler is going to identify these casts, and in that case, the integer type that's at least as large as the pointer width is going to be replaced with a different representation that's a union of an integer or a pointer. The evaluator can implement this trivially because AP value is already a union of, AP value is already a union of everything that can be represented in C++.
Okay, thank you.
Looks like that's all the questions we have. One more question?
So I am working with architectures that have odd properties, like 20-bit integers or 16-bit characters and so on. Will that also be handled?
Yes. So the interpreter has some built-in types, 8, 16, 32, 64-bit integers. But if an integer is classified as having a funky bit width, then the implementation falls back onto AP value. It won't be fast, but it will work. And if you want to make it faster, then a wrapper could be built. To represent a 24-bit integer using a 32-bit integer, making sure to clamp whenever needed.
Okay, thank you.
And if that's all the questions we have, we could thank the speaker.